Our next speaker is Annabelle Bohrdt, and she's going to talk about connecting numerical methods, quantum simulation, and materials.
Okay. Yeah. Okay. I think I forgot to. Should I turn this around? Can you hear me well? Yeah. Okay. Let me make this small, and I forgot to bring a clicker, but I think I'm good without. So yeah, let me start by thanking the organizers for having me here. I've learned a lot already, and I think I'm going to maybe break the context a little bit by going into more of a methods direction here. So I want to tell you a bit how we come from a numerical and quantum simulation side. So we already had Pedram now, and I think we have some more quantum simulation talks today. And we now have a lot of different platforms for quantum simulation. So we've heard from Pedram about the superconducting qubits. Sorry, Pedram, I have the IBM picture here. There is also, for example, tweezer arrays, I think, about which we will hear in the next talk, trapped ions, cold atoms, and optical lattices. And I want to tell you a bit how we can combine this now with numerical methods, in particular neural networks, to make the most out of all of these methods. But let me maybe, in the spirit of what we've heard today, start with what we can measure with these new experimental platforms. So, okay, I think the left side, I don't need to really say anything about, but on the right side, when we do a numerical or a quantum simulation of our microscopic model, we in a way have more freedom of what we want to do, because in principle, we can, of course, emulate solid state experiments to try to directly compare to the measurements that people do on real materials. But on the other hand, we also have the freedom to construct new observables. And I think Pedram and Nandini also, to some extent, gave some examples about that. And let me also give a slightly biased I don't know, collection of examples of what you could measure. So typically the measurements that quantum simulation experiments do are quantum projective measurements. So you get an image out like the one that I'm showing on the top here. So this would be for a 1D Fermi-Hubbard system. And you basically literally see, in this case, this is a cold atom realization. So you literally see whether an atom is sitting there or not. And they basically split it up such that the upper leg of this ladder would be whether you have a spin up and the lower leg would be a spin down. So this is just an imaging procedure. And now from a lot of these quantum projective measurements, you can go and evaluate basically whatever you want. So in this case, for example, this was for a 1D Fermi-Hubbard chain. And they looked at basically a string correlator where they more or less make use of spin charge separation to see the spin-spin correlations extend over a longer range than they would otherwise if you just do it directly on the images. But for example, in the 2D Fermi-Hubbard model, you can also go and look at higher order correlation functions here, what we like to call the magnetic polaron. So you basically go, you dope. So this is a full doping scan, which is also something that you can nicely do. And here, for example, they went and looked at a given hole, what the spin correlations next to the hole would be. So this means you can basically directly look at how the charge degrees of freedom influence the spins in their direct neighborhood. And something that I've worked quite a bit on is to use machine learning tools to analyze these images. So this is very nice, and this is stuff that you can do with this data. One of the huge problems that we have here, and this is now talking about cold atoms, in particular cold fermionic atoms and optical lattices, is that these cold atoms are rather hot. So this is a sketch of a phase diagram. It's a bit outdated. I made this for this review and I should update it, but the key message has not changed, which is maybe quite the message from this. So this now it's 2024, but so the main point is you have this phase diagram here, you have the doping on the x-axis, you have the temperature on the y-axis, and all these stars and arrows are where the cold atom experiments are. And now there is this break in the temperature axis, and they are all at rather high temperatures. And I don't know if Markus is coming, or maybe he has something new to tell about this. So Markus Greiner, but as far as I know, we aren't really below his experiments from 2017. So this is really the coldest they've gotten yet. So we are not quite in the ground state, which on the other hand, maybe for a theorist like me is good news because there's still something to do and it's not all in the quantum simulator yet. Okay, so as an outline of what I want to tell you about in the next, actually let me move this so I can see the time. Perfect. In the next 20 or 25 minutes or so, I want to tell you about neural quantum states. I don't know if this is something that people here have heard about or care. Has anybody heard about these? Okay, that's good, very good. Okay, so I want to introduce what we can do with them, what my group specifically does with them, and show you some results of what we can do to numerically simulate the systems that we care about. And in the second part of the talk, I want to tell you a bit about somewhat new observables, somewhat motivated by what you maybe can do in solid state experiments. Okay, so let's start with the neural quantum states. And so this is, okay, I assume all of you have heard about matrix product states, right? So for a matrix product state, the key goal, what you want is, like typically what you want is you want to represent a quantum state of interest. Often this is the ground state of a Hamiltonian. So what you start out with is a Hamiltonian, and you want to find the quantum state which minimizes the energy of this Hamiltonian. And so basically, in a way, you have a kind of optimization problem that you're going to solve. And the idea of neural quantum states is somewhat similar to that. So the input to your network would be a configuration. So for example, a configuration in Fock space, and the output would be the corresponding wave function coefficient. So you parameterize your quantum state, but instead of for a matrix product state, you would do a product of matrices, as the name suggests. Here, your parameterization is in terms of a neural network. And of course, now if you go to a somewhat larger system, you have a lot of degrees of freedom. The dimension of the Hilbert space grows exponentially. So you have a larger number of degrees of freedom of your system than what you can reasonably put as variational parameters into your state. But the whole idea of neural networks is, of course, that you are very well in approximating general functions. So the idea is using less parameters and putting these parameters in the form of a neural network, you now encode your quantum state. And you can do now whatever architecture you want. I'm putting maybe the two simplest that you can think of here, a feed-forward neural network and a convolutional neural network. But of course, you can do whatever architecture you want to do here. And this is a method that was introduced only 7 years ago. And we also wrote a review article, which might be hopefully useful if you want to learn more about it. Okay, but the main takeaway at this point is that you can also, if you want to treat your neural network as a black box, you put in, say, a Fock space configuration, and you get out a wave function coefficient. And by doing this, you have a representation of your quantum state. And this you can now use to do whatever you want. So for example, you can try to find ground states. You can reconstruct a state from data. You can do time evolution. You can look at open systems. You can do finite temperature states. So you can see there's a lot of stuff that you can do in principle with these neural quantum states. What I want to focus on today is mainly finding ground states with some state reconstruction. Okay, so at this point, you might be wondering, why do these neural quantum states and not, for example, some form of tensor networks? And the reason is that there is strong reason to believe that the neural quantum states capture more, have a higher representative power than, for example, matrix product states. So if you take all of your quantum states, then there's reason to believe that the neural quantum states can capture more of these quantum states than, for example, matrix product states can do. So early on, there's been, for example, work, and I specifically put this because the context of this workshop is entanglement in quantum materials. And so we know that matrix product states, the limiting factor in a way is the entanglement of your state. And fairly early on in this field, it was shown that in principle, and okay, here they are talking about RBM, so just think of this black box because you take different architectures and prove different things for different architectures. But they show for these restricted Boltzmann machines that they can, for example, represent volume law entanglement. So this is good. So you can represent, in principle, you have the capability to represent a lot of entanglement. This is not necessarily a limiting factor now. Another, I think, very relevant work in this context is that if you take any matrix product state, you can, in principle, take that matrix product state and represent that same state as a neural quantum state. So if you have any quantum state that you can represent as a matrix product state, in principle, you can also represent as a neural quantum state. And this is the reason why we drew the sketch the way it is. So anything that's in the orange matrix product state bubble is also in the blue neuroquantum state bubble. But I will get to the problem with that in a bit. But of course, there has been a lot of also, I mean, this was sort of somewhat theoretical proofs, but there has also been empirical work that shows this. So for example, for J1, J2 or Heisenberg models on a square or triangular lattice, people have just done this search for the ground state of these models and shown that at least if you make your system large and 2D enough, you get to lower ground state energies than you get with, for example, DMRG. And so this is very promising. And the way that you do this is literally variational Monte Carlo. So you have your quantum state psi theta. So the theta are your network parameters. You can now evaluate the energy, so just the expectation value of your Hamiltonian. And you know by the variational principle that this energy will always be larger or equal to the ground state energy. So you basically just try to make this energy lower and lower. So you basically do gradient descent, changing your parameters theta, which are all of your neural network parameters, such that the expectation value of your Hamiltonian gets lower and lower. So this is what you do if you want to find a ground state. And in principle, this should be great because we've seen these theoretical results that you can represent a lot of states with these neuroquantum states. The problem is now there's in principle two things, right? One is that your parameterization, in this case, the neural network, can represent the state that you're interested in. But the other problem that you then face is that you actually have to figure out which variational parameters to put such that you represent the state of interest, right? So it's not only that you can, in principle, represent the state, but you also have to find the specific parameterization of that state. So here is an example for a 4x4 TJ model. So this is something that we can still do with exact diagonalization. And that's why we looked at it, because we have like an exact point of comparison here. And on the y-axis of this plot, I'm showing the number of parameters. So this is the number of variational parameters in my ansatz. On the x-axis is basically the hidden dimension. So this is how we tune this within this specific network architecture. And so the gray lines is our neural network quantum state. And these blue lines is the actual Hilbert space dimension of our system. And so if you just look at the dark blue lines where it says NH equals 1, this means that we just have a single hole in the model, which gives us this like Hilbert space dimension of, I don't know what it exactly is, but it's right there. And you see that the 2 points to the right of it, of our neural quantum state, have a larger number of variational parameters. So this means, independently of all that I told you before about volume law, entanglement, and representational power and whatnot, now I'm using a neural quantum state and I give it more variational parameters than the Hilbert space dimension of my problem. So independent of how well my neural network can, interpolate in the larger Hilbert space and so on, I just give it enough variational parameters to represent my quantum state of interest exactly. But the issue is it's not working so great. So basically, if we do the training and try to minimize the energy, I'm plotting now the relative error of the energy. And the red line is the TJZ model that works better, but the TJ model is the blue line, and you see it's okay, it's not bad, but the error, the relative error in energy is on the % level, which is not great, given that I have more parameters than my Hilbert space dimension. And so what this shows you is that even though your neural quantum states can represent a lot of interesting states, and they are very promising, you still have to deal with the fact that you don't have DMRG, basically. So you don't have such an efficient optimization algorithm, and you really have to find that minimum in your optimization landscape somehow. Okay, so this brings me to the hybrid approach that we're using. And here the idea is that we do have all of these quantum simulation experiments. And for now, so the next part will be mainly on spin-on-half systems, just because you have to start with something. And sometimes it's a good idea not to start directly with interacting fermions. But the idea is now we have all of these quantum simulation experiments, and they provide this data. They provide these projective measurements, but often these are not perfect. I showed you this Fermi-Hubbard phase diagram. They are fairly hot, but also for spin-on-half systems, you do have to prepare your state somehow, and often there is, quite some defects in those states. So typically you are in one way or another at an effective temperature in those systems. So the idea is now to take this data, which is not quite the ground state, but fairly close to it, from a quantum simulation experiment, and first do a state reconstruction. So we first, as a cost function, in this data-driven training part, we now try to really only get our neural quantum state to represent the data distribution from the data that we get from a quantum simulation experiment. And then in the second part, in this Hamiltonian-driven training part, we switch our cost function. So now we are no longer trying to represent the data that we got from a quantum simulation experiment, but instead now we put in the Hamiltonian and we try, as before with variational Monte Carlo, to minimize the expectation value of that Hamiltonian. So the main idea here is that instead of starting somewhere in our vast parameter space, we use the data from the experiment, which is fairly close to the ground state, to initialize us in a good point in this vast parameter space, such that subsequently, when we do our variational Monte Carlo, we already start from a somewhat physically motivated and very good starting point, which hopefully helps us to actually reach this minimum of our loss landscape. Okay, let me show you one example where we did this. So this is now a dipolar spin 1/2 model that's realizable in these Rydberg-Tweezer arrays, in this case in Antoine Poirier's group in Paris. So I put the Hamiltonian up there. And what I'm showing you now is the energy of our neural quantum state versus the DMRG energy. So in this case, we used DMRG with a lot of parameters as our benchmark. So this number, this energy difference should go as low as possible. And I show this as a function of the training steps. And in this first gray shaded area, we train on the data. And we also compare training on, how should I say this, exact, like defect-free numerical data and experimental data. So this is the blue and the red lines. And the gray line is just doing variational Monte Carlo, so not doing this hybrid approach. And then after these first 500 training steps, we're in the hybrid approach, we try to get just represent the data distribution as well as possible. In the second step, we do in all cases variational Monte Carlo to lower the energy of our Hamiltonian. And what you see now is that if we use any data, independent whether we use numerical or experimental data, we end up in the end of our training at a significantly lower energy than if we were to just do variational Monte Carlo. So this means we can really put ourselves into a better spot in our loss landscape to reach convergence and really not get stuck in any other local minimum here. And maybe the thing that I actually personally find most incredible about this is that the data is not so great. So I'm showing here just as an example on the x-axis, we are tuning now a Hamiltonian parameter. So for example, this is this delta, let me go back. So this is this field, the staggered field that they have on here. So we are tuning this as a Hamiltonian parameter. So each of these symbols now, like each of these delta values is a separate simulation. And what we're looking at is spin-spin correlation functions, sigma x on the left plot and sigma z on the right plot. And the so the green crosses, dark green crosses DMRG. So this is what you get if you run DMRG with a lot of variational parameters. And this is sort of what we think we should arrive at in the end. And the light green crosses is the experiment. And what this shows you is that the experiment is really fairly far away from this ground state. So, I mean, they did a great job. I mean, these are very challenging experiments, but the state that they are preparing, I mean, for example, for the sigma x correlations on the left, you can see that the spin-spin correlation is roughly half of what it should be, right? So, I mean, if I run numerics and this comes out, this is not great. So this is the, yeah.
This is only wave function.
Yes, well, yes, so, yeah, that's a great question. So, I guess you can discuss whether you call this a finite temperature, because what they in principle do is they start from a product state and they do a parameter ramp. And then at the end of the parameter ramp, they kind of hope they did it adiabatically and stayed in the ground state. So it's not necessarily equilibrated, but I would say it's more or less equivalent to a finite temperature state because it's not the ground state of the system. So I would say the issue is not necessarily that it's like in truth a density matrix versus a pure state, but the issue really is that the experiment is not in the ground state. Okay, and so the experiment is somewhere down there, you can also see that if we use the neural quantum state and only do VMC, we get these gray symbols. So you see that's also better than the experiment, but it's still not great. And now sort of the amazing thing is that if we combine these two things, which are both not perfect, so if we combine the light green and the gray in this hybrid approach, we get these red symbols, which are really much better than both of the things that we combined to get there. So this tells us that even though numerics may struggle, in particular these neural quantum states in the optimization procedure, and experiments may struggle because they are not perfect in preparing the states that we really care about, that when we combine these two things, we can really reach the realms that we are interested in. And now we're using DMRG as a point of comparison for this specific model because we can still do DMRG. But what I also want to highlight is that we are using significantly less parameters. So here we are plotting the energy minus the energy at the highest bond dimension for the DMRG, so at the largest number of parameters that we were considering. And on the x-axis on a logarithmic scale, we have the number of parameters in our variational state. And so basically actually, let me use my mouse, maybe this is the easiest thing. So you can see that as we increase the bond dimension, these are all DMRG simulations, and as we increase the bond dimension, the energy goes down, as it should. But if we want, for example, so these are different colors are different values of our Hamiltonian parameters. And if we, for example, for this yellow symbols here, want to reach the same energy accuracy as we have here for this MPS, we already use something like 10 to the 7 parameters in our matrix product state approach, whereas for our neural quantum state approach, we get away with 100 times less, so 10 to the 5 parameters. Yeah, okay.
One step back, so you were training, pre-training, or what do you call it, in both of these on some number of snapshots, right? How many snapshots are you DMRG into the description?
Right, so the DMRG does not use any snapshots. The DMRG is literally only DMRG. Okay, maybe this. Yeah. Yeah. So both of these, actually, I kind of swept this a bit under the rug because we do two things here. So we use snapshots, but we also use 2-point correlation functions. And we use typically something like between 100 and 1,000 snapshots to train on. More would always be better. I don't have this in here, but you can see that the lesser snapshots you have, the more that you overfit, such that if you just look at your energy while you try to represent the data distribution, the energy at some point starts going up again. So more would always be better, but it's quite amazing that fairly few are enough. And actually, since you already asked about this, what this experiment had a big advantage, I mean, I'm also showing this on the next slide, is that they measure both sigma x, and sigma z. So they have these projective measurements and they have them in the z and in the x spaces. I'm highlighting this because for example, for a quantum gas microscope, this is not something that they standardly do. And now, of course, since they had them, we also wanted to use both of these basis measurements. And this is a somewhat important point because if you only use the z basis measurements, in a way, you don't put any phase information into your state, right? So you're only learning the amplitudes, but not the phases. And you can imagine that if you have a complicated optimization problem like this and you ignore the fact that your wave function coefficients are complex, this might not help so much. And this is why we basically use snapshots in the z direction and 2-point spin correlations in the x direction. And already, even if we didn't have any snapshots, but just use 2-point spin correlation functions, that would already give us an advantage, which I think is pretty nice. And actually, compared to snapshots, the 2-point spin correlation functions also have the advantage that you can average, or you can basically average over your 100 or 200 or whatever snapshots, and you get a somewhat cleaner signal in them. Okay, so here I was showing you that we basically can do all of this with significantly less parameters than what our matrix product states need. And now our obvious next step is to go away from our spin-on-half models and go back to interacting fermions. And the next, in my opinion, logical thing is to look at TJ type models. And so this is what we are currently working on. So Hannah and Annika are looking into a TJ model. This is now for a 6x10 system. So it's already, I would say, fairly large. And now this is the worst case. So this is if you have exactly 2 holes. For some reason, we do a full doping scan. For some reason, 2 holes is the hardest thing for the neuroquantum state. So this is kind of the worst case scenario. And again, you're looking at the relative error compared to a highest matrix product state bond dimension that we use. And we are looking at the x-axis on the number of parameters. And you can see again, so if we want to reach the same accuracy, for example, here we have a relative error of something slightly above 1%. If we want to reach the same accuracy with the matrix product states, we have to do something like a factor of 100 or 200 more parameters in our matrix product state. So this is really something that once the universities buy more GPUs, we can, I think, really run simulations at much larger systems than what we can currently do with Eumergian matrix product states. Okay, and also let me not just show you energies, but also some physical quantities. So here we are looking, for example, at the spin-spin correlation functions for nearest neighbors and diagonal next nearest neighbors as a function of doping. And I was quite excited when I saw this plot because, I mean, you don't every day do a full doping scan of your spin-spin correlation functions. And we did sort of the same thing with Emanuel Bloch's experiment a couple of years ago okay, this is now the Fermi-Hubbard model. This is at finite temperature, but you can see it shows you something similar. So for example, there's the zero crossing of the next nearest neighbor spin correlation function at around 20% doping, for which we have some physical picture. And you also see this now in these ground state simulations of the TJ model. And you see that they have the TJ model, our simulations are now at a level where we can really start looking into the physics of these models. Okay, good. He's getting up. I have a second part on the Hubbard excitons. Maybe let me just talk to you for 2 minutes about what this is about. So this is now, since I was using this a bit as a punchback, but we also do a lot of matrix product state simulations, and all of this is using matrix product states, in particular time-dependent matrix product states. And the idea here is to be somewhere, I would say, in between these two things, where we are still motivated by solid state experiments, but we are also thinking about what else we can do or what more we can do. And the idea here is to look at a spectral function, but not of a single hole, but of 2 holes. So we want to basically punch 2 holes into our system. And now you have different ways how you can punch 2 holes into your system. You can put them in plus x plus y minus y direction and so on. And by adding a phase for these different configurations, you can put pairs with a certain angular momentum. And what we are looking at now is a singlet excitation. So we take out a singlet of our system and we take out a singlet with a certain M4 quantum number. So a certain angular momentum, which can be for our square lattice in 2D, it can just be 0, 1, or 2, or S wave, P wave, or D wave. And what we saw for just the TJ simulations is that basically we get 2 different pairs. Depending on whether we create a D wave excitation, we get this strong spectral weight, but the dispersion is pretty flat. Whereas if we are looking at an S wave pair, we get a much steeper dispersion. So this, we ran some different scans. So this here goes with J, whereas this here goes with T. We also have a fairly good understanding of this in terms of this geometrical string theory picture. So this is a semi-analytic theory, which basically calculates the same thing. It's just black and white. This is what Fabian does. I have colors. And this is the same thing for the M4 equals 2 here. So this is very nice because we have the numerics for the TJ model. We see that we can get heavy and light pairs in the TJ model. And we also can really explain this in the context of a semi-analytical picture. The only issue now is that this is really a numerical thing, because this is not only hard in a solid state experiment, this is also hard in a quantum simulation experiment, because even if you can do a lot of isolated dynamics and have a lot of, like power of manipulation over your system, making 2 atoms go away in a coherent fashion is hard, right? So this is what we really want in this pair spectroscopy, because we want to take our 2 atoms next to each other in a very well-controlled way. And these 2 atoms have to go somewhere. But what we realized is that in principle, if you have a Fermi-Hubbard system, instead of taking 2 atoms out, you can also put 1 atom on top of another one. So now we don't have 2 holes, but we have 1 hole and 1 doublon. And this is an exciton. And now it turns out that a lot of the properties of this Fermi-Hubbard exciton, which exists in this Fermi-Hubbard-Hilbert space, you can really explain or are the same properties that you get if you put two holes into a TJ model. So this on the left here is now this spectral function for this Hubbard exciton. And on the right, we're looking at two distinguishable dopants in the TJ model. And you can see, okay, one thing that you can see is that the resolution is slightly better for the TJ, but you can see that a lot of the features that we get are the same in both of these spectra, right? So if, for example, you see this band goes here and there is the same thing up here. So you can see just by eye already visually that these share a lot of the same features. And these distinguishable dopants we can now split up into symmetric and antisymmetric part of the Hilbert space, or equivalently a bosonic and fermionic pairs of charge carriers. And again, both of these we can then explain with this geometric string theory. So this is very nice because we basically look at a pair of dopants. We know that there should be some exciting properties like how fast do these pairs travel through the system and so on. And we think in principle that you can measure these Hubbard excitons also in a quantum simulator if you just make one atom hop on top of another one. And then one thing that we also found is that there is Riggs experiments about which we have heard a lot, where basically, and I don't want to make too strong assumptions about this, but basically if you literally just take these Riggs data on the parent compound, so this is the undoped cuprate parent compound, and you just take this Riggs data and you put it on top of the exciton spectra, you see that it actually agrees extremely nicely. So you also see that you basically, so you get these peaks here in the D wave in the M4 equals 2 exciton spectra. And this is basically something like excitations of the string object. So we have a good theoretical understanding of what they are, but you also see them in this Riggs data. And at this point, you might be saying, okay, this is just one line, but you can do this for all momenta. So this is now going from 0, 0 to, I think, pi 0. And then, of course, there's also another cut that you could, in principle, do. And you see that for all of these momenta, this agrees extremely nicely. And there's only one fitting parameter, which is basically the overall energy shift that we do, which in principle is just U over T in these models. Okay, with this, I'm like way over time. I told you about the neural quantum states and the pair and the excitonic properties. Let me thank the group and in particular the people involved here. I think Fabian will tell you also something probably very unrelated later today. And with this, let me thank you for your attention.